Okay, what we're going to be doing in this video is having a look at wave speed problems, questions 6 to 11, which are these ones that I gave you in class. We're going to work through the answers to these. So take note, pause the video as you need to. Now what we're going to need to do in this particular video is use a formula that we haven't been given in class, but it's pulling on a bit of prior knowledge. It's covered here. So speed is equal to distance divided by time. So you might have covered this at GCSE level before. So we put that over to one side just there. So problem 6. Firstly, this talks about tsunami waves rather than rogue waves, which we covered in problem 5 in the previous video. And what it's asking you to do is to determine the speed of the wave, firstly in miles an hour and then in meters per second. So what we're going to do to start with is understand that speed, and this can relate to the wave of a speed, is equal to the distance that it covers divided by the time it takes to do so. So the distance is 6,200 and we divide it by 15 to get this into essentially miles per hour. Okay, again, use my calculator. 6,200 divided by 15, so it's moving at 413.3 miles per hour. Okay, now the next thing that we realize is that the question gives you some information that 1 meters per second is equal to 2.4 miles an hour. So to convert this, so to go from miles an hour into meters per second, what we're going to do is divide by 2.24. Again, you're not really going to be tested on this in the exam. This is just making you able to make sure you can use formula and that you can do conversions. So don't panic too much if you don't know that already. So 413.3 divided by 2.24. Again, we put that into the calculator. Gives us 184.5 meters per second, and that's our answer there. So that's problem 6 solved. Problem 7. Again, this one using the same kind of concept. So this talks about seismic waves, which we know are P waves, longitudinal, detected approximately 990 kilometers from the epicenter. So that's how far it's traveled. And we know that they've traveled at 6.3 kilometers a second. And we need to work out the time delay. So in this case, we know that velocity or speed is distance over time. So time is therefore equal to distance divided by velocity. Now distance we know is 990, and we divide that by 6.3, and it gives us 157.14 seconds. So that's the time delay between the earthquake and its position 990 kilometers away. So it's moving extremely quickly in that example. So there we go, that's the answer to that one. Problem 8. Problem 8 is about bats. Bats use echolocation. So what they do is they emit high frequency sound waves that bounce off objects, and they can detect the distance they are from an object. In this particular case, the key thing we need to know is that the pulse hits an object 12.5 meters away, and the speed of that wave is 345 meters a second. What it's asking you to calculate is the time delay. So again, time is going to be equal to the distance divided by the velocity. So the distance in this case is 12.5 meters, and we're going to divide that by 345 meters per second. So 12.5 divided by 345. So this gives us 0.036 seconds. So those bats are working extremely quickly in the way that they're detecting things around them, and they have adapted to do that. It's incredible how quickly they can work in that sense. What I'm going to do is just quickly get a blank page. Okay, so the next one, question 9. This one works on the basis that you've got essentially a snaky or a slinky. So this is like the long slinky that we've used in class, and you've got two people at either end, and they shake the slinky and it makes a wave. And they're made of two things, essentially. One's made with copper and one's made with zinc. And they are measuring a gap of 6.8 meters. So from one end to the other is 6.8 meters. And we can see that the first measurement, using a stopwatch, Abby measures that it takes 15.1 seconds for the pulse to travel to Cassie's end and back 2 times. So that means it goes there, back, there, and back. So that's actually 4 lots of the distance. Okay. They then repeat the experiment. So what we need to do at this point is determine the speed of the pulse. So there's different ways of doing this. The way I would probably suggest doing it is multiplying the distance by 4. So that would be 6.8 times 4. 6.8 times 4. So that is, so it's travelled a total distance of 27.2 meters. And the first one, so A, took 15.1 seconds. So again, what we're trying to calculate here is speed or velocity. So distance divided by time. So in this case, it's 27.2 divided by 15.1. 27.2 divided by 15.1. And that gives us 1.8 meters per second. And then B, velocity is distance over time again. The distance is the same, but this time it takes slightly longer, 16.9 seconds. 16.9. So again, we calculate that 27.2 divided by 16.9, and that is 1.61 if we round up meters per second. So those are our 2 values. So we can see that the wave is moving faster in the zinc coiled Snaky, okay, or Slinky if you prefer. Number 10. Number 10 gets us back into the realms of what we're actually needing to know for the exam. So again, we're going to be needing these formulas here, specifically this one. So V equals F lambda. Okay, so the first bit, what we have is about a radio station, which is 102.3 FM, and that's not really useful to us. We don't need to know that. So again, not important. What we understand though is that we have a frequency of 1.023 times 10 to the power of 8 hertz, and we have a speed which is V of 2.97 times 10 to the power of 8, which those of you who know would know that as the speed of light, because remember, radio waves are light waves, and we are trying to determine the wavelength, or lambda. So V equals F lambda rearranges nicely into lambda equals V divided by F. So in this case we do 2.997 times 10 to the 8 divided by 1.023 times 10 to the power of 8. Now there's 2 ways you can do this. You can type it all into the calculator, like so, 2.997, and I would make sure you use brackets, times 10 to the power of 8, and then you can use a double bracket if you want to neaten this up, divided by 1.023 times 10 to the power of 8, and it gives you a value. Alternatively, you can just cancel out these bits and then just do this as a division, okay? And so as you can see, the answer here is 2.93 rounded, 2.93 meters. If we just do this, 2.997 divided by 1.023, it gives the same value, okay? So that only works if these two numbers here are the same, and you can cancel them out. If this was a 7 or a 6, then you would need to probably use a calculator or have some other way of working out using arithmetic. But that is the answer just there. So that's the wavelength. Now the last question, number 11. So is a transverse wave. There we go. We draw a transverse wave, observed to be moving along a rope. Crests are positioned, so there's a crest and a crest and these are measured to be 2.4 meters apart, and then there are 6 waves, which is there, 6 crests are observed in 9.1 seconds. This question asks you to calculate the wavelength, the frequency, and the speed of the waves. So the first thing that's really easy is lambda. Lambda is right there. First marks in the bag. So wavelength is 2.4 meters. The next one that we're going to do is we're going to calculate the frequency. To do this, we're going to need to follow these formulas here. So firstly, period. So let's work out the period of the wave. So the period is going to be equal to the time, which is 9.1, divided by the number of cycles, which is 6. So again, we get our calculator and we calculate that to 1.52, which is rounded. We can round here. That is the time period for one wave, and then we do the frequency is 1 over 1.52, 1 over 1.52, which is 0.66 hertz rounded. Now we have a frequency and a wavelength. So it's as simple now as going V equals F lambda. So that is 2.4, sorry, times 0.66, 2.4 times 0.66, 1.584 meters per second. And there's your answer. And that's the answers to the problems 6 through to 11. And that concludes this video. Thank you very much.